Hello, everyone. This is the third in a series of lectures about Chapter 15. We are going to begin by formally defining simple harmonic motion, which we have already been talking about for the earlier recordings. For an object to be moving in simple harmonic motion, it simply means that its acceleration is proportional to its position, and also that the acceleration is opposite in direction from the displacement of equilibrium. So we have already seen this in the spring block system, where Hooke's law described that the force and therefore the acceleration is always the opposite direction to the displacement. So it's proportional to displacement, but also there's a negative sign in the formula, meaning that it'll always point the other way. Now, in the real world, we have, of course, springs and other similar objects that can oscillate. And while there's multiple sort of forces acting on them, not just a restoring force, we can begin by modeling these objects in the physical world using the simple harmonic motion model, and there start adding, effects such as damping or drag. So if we look at a few examples, somebody in a bungee rope will jump out of a bridge, and the rope will become stretched and tug the person up and down for a bit. So there's a period of time where the rope kind of acts like a simple harmonic oscillator in the sense that it's kind of tugging up and down. Obviously, there's also drag from air resistance. Eventually, you come to a stop, but there is a motion there that is like simple harmonic motion. Another example is when you pluck a guitar string, the material in the string vibrates in simple harmonic motion. Another example is actually vibrating molecules. So when you have two molecules bonded together, by which I mean two atoms bonded together into a molecule, they vibrate as if they were connected by a spring. So you can model that with simple harmonic motion. In fact, you don't necessarily have to have a spring, right? Simple harmonic motion, like you saw, can be undergone by a guitar string or bungee rope. So you can actually say that a particle is undergoing simple harmonic motion as long as it meets the conditions that it has an acceleration proportional to its displacement from equilibrium, and that it's always in the opposite direction. So as long as you know that an object is undergoing simple harmonic motion, you can always describe its displacement with the Coase formula we've seen before, and its period and frequency can be defined accordingly. Now, the angular frequency, of course, in the case of the spring block system, is a function of the mass of the block and the spring constant k. But for other oscillators, of course, the angular frequency will be a function of something else, which we'll see a few examples of a bit later. First off, I want to talk about the energy of a oscillator, because after all, if it's moving, it must have at least some kinetic energy, right? And we talked about in kinematics last year that the kinetic energy of an object in motion is 1/2 mv squared. So we can apply this formula for a oscillator. So think the mass spring system. And in this case, because we have simple harmonic motion, we can actually substitute the speed term in the kinetic energy formula for the full function for speed as a function of time. So we can end up with a sine square there. and all the terms we've seen, the amplitude and the angular frequency and the phase shift phi. So that means then that the kinetic energy changes periodically with time. So at the point where the oscillator passes equilibrium, the max kinetic energy is, the kinetic energy reaches its maximum value when you pass equilibrium. After all, that's when the speed is maximized. But when you reach the points of max amplitude, A and negative A, that's when the kinetic energy is zero. If you think back to the spring block system, that's when the block comes momentarily to a stop as it's in a state of full stretch or a full compression. So it also means that there's what's sometimes called spring potential energy, which an oscillator has, and that depends, for the case of a spring block system, depends on the spring constant, and also the potential energy depends on the position. So for a simple harmonic oscillator, the position, cycles, and therefore the potential energy that it has stored changes over time. But essentially, the more compressed or the more stretched the system is, the more potential energy it's storing. Because potential energy, like we saw in the case of gravitational potential energy, it's the ability for a force to do work. It's at the point where you're stretching or compressing that the restoring force gets bigger and bigger, and therefore can do more work on the oscillator, or on the spring block system to be specific. So then the kinetic energy, the potential energy is maximized at the points of full displacement. So when x is at the full amplitude of oscillations, but when you pass through the equilibrium position, the potential energy is zero. So the previous slide is not relevant to this video, so we'll just pass over. It's just like a bit of a extra math explanation of how some formulas are derived. Anyhow, the graph here, the three graphs kind of show the starting position of an oscillator. So the block starts at a full stretch at an amplitude of A. And at this point, right, the acceleration is maximized. We're about to launch off all the way to the left. So we are not moving just yet, and thus all the energy of the spring block system is in the form of potential energy. Now, as soon as we let go, we'll start flying off to the left, and in about a quarter of a period, we'll pass equilibrium. When we do so, for that brief moment, we're neither compressed or stretched, so we don't have any potential energy. That energy is transformed entirely to kinetic energy, so this is the point where we achieve the maximum kinetic energy. As we keep going, though, we'll compress all the way, and we'll reach an amplitude of negative A. So at this point, we come to a brief stop before we launch off again. So we've lost all the kinetic energy that we just gained while passing through equilibrium, and traded that for potential energy. And again, this exchange happens throughout the cycle. So over time, one increases while the other decreases, and back and forth. And then for the rest of the cycle, then the block will accelerate to the right and pass equilibrium again, as you see in graph D. So at this point, we are 3/4 of the way through our cycle or period. And again, we're passing equilibrium, so it's all kinetic energy here. And then finally, we'll complete the period in graph E, where now we are fully stretched again, about to accelerate all the way to the left, and we have only potential energy at this point. Graph F just shows you the system at any particular position at any particular time. So basically, as long as you're not in equilibrium or at the full amplitude, you always have some kinetic energy and some potential energy. So both kinetic and potential energy are essentially functions of time. So if you graph them, you see how over time, over a cycle, they sort of interchange. In the graph on the right here, we see that we start off with maximum potential energy, and then over a quarter of a period, we drop off, while in that time, the kinetic energy has been maximized. So this is essentially starting from a full stretch all the way to the equilibrium point. And then once you get to the halfway point of the period, that's when we reach like a full compression. So again, we lost all kinetic energy and now it's all potential. But then you see as we swing back to the right to a full stretch to complete the period, the energies exchange again over that period of time. So if you remember the formulas from before, right, you can write the kinetic energy as a sine function and the potential energy as a cos, which means that they would be a quarter period or a phase, which is what we see in the graph here as well. Also, if we were to just plot them as functions of the displacement from equilibrium, we see that they take on a parabolic shape. So as one gets bigger, the other decreases and vice versa. Now, because this is an ideal mechanism without any drag or friction, the total mechanical energy of the system is conserved. And that means that at any point in time throughout the motion of this mass block system, the total energy is constant. So whatever potential kinetic energy you have at a particular point in time, that has to add up to the total energy. So the total energy can always be calculated by the formula 1/2 k amplitude square. And from this formula, you can actually derive it to have a formula to quickly calculate the speed of your oscillator at any particular displacement, which is shown at the bottom of the slide. That's all for this lecture, and I hope you join me again in lecture 4.